So in this video, we have a CD that's being spun at 30,000 revolutions per minute, and the stress due to the extreme rotary force can actually cause a significant mechanical stress within components, and that mechanical stress can in this case, but even in some engineering components and they're very very high RPM, can cause the system to vibrate and eventually shatter. So these stresses need to be accounted for when we're designing components that are undergoing rotary motion. So today we're going to talk about those stresses in thick-walled cylinders. So we talked about earlier in the last lecture, we mentioned the you mentioned that he, you mentioned a case where we had um, um, in a case where we had no rotation. In this case, if we do have rotation, all right, um, all right, but we have no external pressures. So the external pressures and the internal pressure in this case are both equal to 0. All right, and we go back to our general equation, which is equation 5.8-8. All right, and okay, our solution to that equation would be these equations here. Okay, because we know that there's no external or internal pressure within our thick-walled cylinder, we can say that the radial stress must be 0 at both the inner radius and the outer radius. Okay, so because we know those boundary conditions, we can plug in those boundary conditions into equation 5.8-27, and we should then be able to solve for the two unknown constants C1 and C2. Right? So if we know C1 and C2, we plug those in, and we end up with these two equations for our radial stress and our tangential stress due to the rotational force. Okay, um, so the one thing I guess I'll point out here is that when you're solving these problems, you should note that many of the terms in these equations are equal. They might just have a difference in the signs in front of them, but it can save you some time in the problem solving if you just if you group those, I guess, solve for those terms individually and then sum them up to get the radial stress and the tangential stress. So for the maximum radial stress due to the external pressure, or sorry, due to rotary motion, is going to occur at when r is equal to the square root of Ri and Ro. All right, the maximum radial stress will occur, and then the maximum tangential stress will always occur at the inner radius. Okay, so this is the maximum tangential stress, and it will always occur when the radius is equal to the internal radius. Okay. So we have in a particular case, if you have a completely solid disk, otherwise known as a shaft, meaning that the internal radius is 0, alright, so we only have an outer radius, you may use the following two equations for sigma r and sigma theta. Alright, so these are just simplified versions of these equations we developed on the last page here. Alright, so we just plugged in basically Ri is equal to 0 into those two equations, and you end up with these equations. Alright, so these are just simplified equations for shafts. Alright, and remember that for the rotor, or the displacement along the radial direction, is still going to just be equal to the same equation here, equation 5.8-17. Okay, Please note that while uh, that if you have a rotating, if you have two components within each other, so let's say you have a shaft, and on the outside of that shaft, you have a disc, and both of these components are rotating. All right, the interference between the two press fit components will change. Essentially, due to the rotary stresses, those components will change. So you need to calculate the modified interference at the velocity. And then once you find the modified interference, you can then solve for the internal pressures and you can solve for the interference pressure. All right, so once you have that interference pressure, you could then use the equations we developed earlier for thick-walled cylinders with internal pressures and external pressures to solve for the stresses within each of those elements.